we have Alan Wolke, W2AEW, and he's going to present using the NanoVNA to perform an antenna analysis with the Smith chart. So without further ado, I'd like to turn it over to Alan. Take it away.
All righty, very good. Hey, thank you for the introduction. Just a little bit about myself before we get started. Actually, I'll share my presentation here in a moment. I'm a field application engineer for Tektronix. I've been a field application engineer with Tech for almost 16 years, primarily focusing on RF applications, but spent over 20 years before that as on the other side as a design engineer, application engineer, and test engineer in various industries ranging from fiber optics to hard disk drives. So, but always been a bit of a tinkerer, and that's mostly what my YouTube channel is about. There's about 165,000 subscribers and a little over 20 million views on the videos that I have up there today. But basically basic electronics and tutorials, test and measurement topics, amateur radio topics, and things like that, and some recordings of presentations like this. So let me get the presentation kind of started here. I'm actually the technical coordinator for the Northern New Jersey chapter of the ARRL field organization, and also a life member of the ARRL. So that's the URL for my YouTube channel right down here. So in case you want to go check it out a little bit later on. So we're going to talk a bit about the basics. I want to give everybody a basic understanding of what the Smith chart is, because it actually can be quite useful, not only to look at what your antenna looks like and making measurements with it, but if you're ambitious enough to go, design a matching network, this can actually help you do that if you enjoy kind of building things, that type of a thing. It's also pretty helpful even if you're using a manual antenna tuner to watch what's going on the Smith chart. And we'll actually see that here as well. So let's get rolling. So the first question is, what is a Smith chart? And it really is a graphical tool that allows you to plot and compute a number of different things. First and foremost, it allows you to plot complex impedance, okay, meaning the real or resistive component as well as the inductive or capacitive component of an impedance. And any non-resonant type of device, including an antenna and the coax and things like that, typically presents a complex impedance to our transmitter. And that's what we can actually go look at versus frequency. I could also look at complex reflection coefficient, and that arises from that complex impedance not being matched to the transmission line, and that creates a reflection. And that reflection has got a magnitude and a phase, which is why we call it a complex reflection coefficient. We're probably most familiar with SWR or VSWR. We can actually read that off of a Smith chart as well. I'll show you how you do that. You can also use the Smith chart, and actually the Smith chart was actually developed to help ease the problem of doing calculations with respect to transmission lines like coax or ladder line or things like that. It was really designed as a transmission line calculator tool originally. So we'll talk about some of the interesting things that happen on a Smith chart with respect to transmission lines. And it also can be used to help you, as I mentioned, design matching networks and really a whole lot more. So we're not going to go into all of these things in great detail. The whole idea here is just to kind of open your eyes a little bit to, what some of the magic of the Smith chart is. Okay, so you understand it a little bit better and maybe dig in a little bit more in those areas that are of interest to you. So let's break it down a little bit. Okay, so the first thing we have to talk about before we get into the Smith chart is something called normalized impedance. And what we mean by that is the Smith chart itself isn't really drawn to represent, like a 50 ohm environment, like for 50 ohm coax. It really can be used in any impedance environment. It could be 50 ohms, it could be 600 ohms, could be 75 ohms, etc. So the way that we use the Smith chart in these various impedances is to do what's called the normalized impedance, where we take the actual measured impedance or calculated impedance, or whatever it might be, and we divide it by our system impedance. Now, for 90% of what we're doing as hams, that system impedance is 50 ohms. So we take our measured impedance, divide by 50, that gives us our normalized impedance. Here, the letter Z represents complex impedance, resistive and reactive component. Okay, So again, for a 50 ohm environment like we're mostly dealing with, we're simply dividing all of those values by 50. So an example, let's say you had your fancy antenna analyzer and it reported that the antenna's complex impedance was 37 ohms resistive plus an inductive 55 ohms of reactance. So the way we normalize that is we divide each term by 50. Okay, so the normalized impedance represented by the little prime symbol would then be 0.74 plus J1.1. Okay, so again, by doing this, by normalizing to the system impedance as being in use, it makes the Smith chart usable for any system impedance. Again, but in our case, it's mostly going to be 50, and that's all we're going to deal with today. And this value here, this normalized impedance, is what we plot on the chart, and that's the way the chart is all drawn. Okay. So the Smith chart itself is really just a fancy graph paper that's all curvy instead of straight. But it's done that way because it aids in a lot of the uses in terms of predicting SWR and what's going on with transmission line lengths and things like that. So the inventor of the Smith chart, Philip Smith, devised this curved graph paper to help ease some of those computations. But it really is just graph paper, all right? And we'll just use it that way. So let's look at the regions on the Smith chart. The horizontal line, you can think of it as the equator, if you will, or what I will call the prime axis, represents purely resistive impedances, no reactance, okay, Jx equal to 0. So any point that's on that middle line, right, across the center is purely resistive. There's no reactive component at all. Now, what's another term for that? Another term for that is resonance, right? Resonance purely means that the impedance does not contain a reactive component, it's purely resistive. So any point along that line is a resonant point, okay? Anything that's above that, this upper hemisphere, if you will, it represents inductive reactance. So if the complex impedance, if the reactive portion is inductive, then that is going to be shown somewhere on the top of the curve, on top of the top half of the Smith chart. And conversely, capacitive reactance is going to be down below. And this, again, when representing the complex impedance, it's the sign of that J term, okay, determines whether you're inductive or capacitive. So anything with a minus J is going to be down here. Anything with a plus J will be up here, okay? So that's kind of, the big picture of how impedance is represented on the Smith chart, but let's get a little bit more detailed. Okay, so where are some key values on the Smith chart? Right smack in the center, right in the bullseye, that represents our system impedance. So in our case, that's 50 ohms. On the Smith chart, it's going to show as 1.0, right? Resistive 1.0 and then J0, right? That's right smack there in the center. That's our system impedance. That's 50 ohms. That's where we want to be, okay? All the way over here at the 3 o'clock position, that represents an open circuit, okay? A high impedance open circuit, very high resistance, and again, no reactance, just an open circuit. So that's represented there at 3 o'clock. At the other end of that prime axis, as you might guess, represents a short circuit, okay? 0 ohms, okay? Just a complete dead short. So you could say, well, gee, we go all the way from dead short to 50 ohms here, and then from 50 ohms to infinity up here. And you can kind of see how that's working with these, with the lines here too, kind of getting closer and closer together. But that's how things are represented on the Smith chart. And it might also, it makes sense to you that, well, it's pretty hard to represent a very high impedance like a 10K ohm or 20K ohm impedance on a Smith chart, because it's all going to be crowded way down in here. So the Smith chart's really kind of usable from a short circuit to 50 ohms up to several hundred ohms or maybe a few K ohms at the very most. And anything beyond that, the Smith chart isn't really that usable anymore, okay, when we're talking about a 50 ohm system, okay? So on the Smith chart, again, there's a bunch of these curves. So what do they all mean, okay? These circles that you see, like you see, I've got this one kind of highlighted in blue, and you see a bunch of other ones that they're all tangent at the open circuit point, and they just get, larger and larger and larger. Those represent constant resistance. The R plus JX, it's the R portion of that that's represented on those circles. The one that cuts right through the center here, that represents normalized resistance of 1, and there, in our case, that's 50 ohms. So this would be 50 plus J0. This would be 50 plus J something. This would be 50 minus J something down here on the curve, right? And then these other circles, like here, for example, that's the normalized resistance of 3.0. Okay, so that would be 150 ohms right there at that point. Okay, now here's normalized resistance of 0.4, so that would be 20 ohms, right? 0.4 times 50. Okay, so that would be that point right there. Okay, so they all represent what we call constant resistance. Okay, so now, and if I expand up on this portion of the axis, we can kind of see there's the 1.0. Let's sit running along that circle. Here's the 0.4 over here. Okay, that's where this circle is. Here's the 3.0, right? That's that one. So it's all these numbers that are kind of here, 2, 1.8, 1.6, 1.4. Those are the numbers that give you the normalized resistive component represented by that circle. Okay. So now the rest of the curves that are on here are these arcs. You see these arcs going up this way and arcs going down that way. Again, they're all tangent to that open circuit point here. But then each of these arcs, and you can see a couple of different families of them in here, represent different values of either inductive reactance or capacitive reactance. So I've highlighted the plus J1 arc and the minus J1 arc. And the values for those are kind of up here. It's a little bit tough to see, but if you grab a Smith chart, you can look at it. There's a 1.0 here, and that's 0.9 and 0.8, etc. So like these lines right here, for example, are plus 0.5 and minus 0.5. Okay, so you can see as we get smaller and smaller and smaller in terms of the inductance, you get to the point where, or the reactance, you get to the point where the reactance goes to 0 and you're collapsed out to this straight line that we talked about. And as you go higher and higher in either inductive or capacitive reactance, you start getting onto these tighter and tighter arcs. Okay. So then, of course, as I mentioned, when the reactance is equal to 0, you're right back to our prime axis going right through the center of the chart. So that kind of gives you a little bit of a picture of where complex impedances lie on the chart. So how do we actually use that? So how would we plot a particular complex impedance? All right. So let's say again that our antenna analyzer gave us a complex impedance of 25 ohms plus an inductive 40 ohm reactance. So the first thing to do is we divide by 50 to normalize it. Okay, and that gives us our normalized impedance of 0.5 plus J0.8. So what we do is we find the intersection of the constant resistance 0.5 circle and the constant inductance 0.8 arc. Okay, so here's our 0.5 circle and here's our 0.8 arc. So we look to see where those two intersect, and that point right there represents that complex impedance. Okay, so again, it's just a graph paper, and we're applying the intersection of two lines. The lines just happen to be curved instead of rectilinear like we have on normal graph paper. But that's actually how you go and plot a complex impedance. So if we look at this from an antenna standpoint, on a NanoVNA, it might look like something like this, right? So in this case, if we look down at the bottom, we started at 13.7 megahertz up to 14.7 megahertz. So this is plotting a little bit wider than the 20-meter band. So I actually see a curve plotted on the Smith chart. The reason for that is because the impedance looking into that, that coax in this case, into the antenna, the impedance changes with frequency. And since we plotted over a frequency here, we're seeing a trajectory, if you will, or a curve representing the impedance that the antenna system is presenting at different frequencies. Okay, so in this case, our complex impedance versus frequency is shown in green. Okay, the frequency is only indicated by the markers. That as on a Smith chart, there's no axis that tells you what frequency you're at. So the only way you really know where you are in frequency is by placing markers on there. Okay. Other plots like an SWR plot or something like that, typically it's SWR versus frequency, for example. And I'm actually showing that here. So this white curve down here, okay, you can see that white curve is actually SWR versus frequency. And I've got a marker sitting right down about the minimum SWR, okay? And the marker on any of the VNAs are going to track on all the traces. So I can see that my minimum SWR is sitting right where that marker is. It says it's about 14.245 megahertz, okay? And that marker is also at the same frequency on my Smith chart curve, okay? So there's my little marker right there. And one thing you'll notice is that my minimum SWR occurs where? At the point on this curve that lies closest to the center of the Smith chart, right? That point lies closest to the center. That's the minimum SWR. So there gives you a little bit of the hint that SWR on a Smith chart is proportional to how close you are to the center of the Smith chart. The further you get away, so like the low frequency end of this curve is way down here, that's the same thing as this point on the SWR chart, okay? So my SWR is what, 2, 3, 4, 5, 6.5 to 1 at that end right here, okay? We're down to about 1.2 to 1 right here, okay? And then all the way at the other end over here, where it looks like we're about what, 2, 3, 4, 4.5 to 1 at that end here. Again, the further you are away from the center of the chart on the Smith chart, the higher the SWR. Okay. So, so how do we actually read that for sure? So on a real Smith chart, which I've got a portion of here, the Smith will also be plotted this set of axes down at the bottom that are called radially scaled parameters. And there's several of them on the bottom of the Smith chart. We're only going to talk about a couple of them here, but there's several radially scaled parameters. So let's say, for example, at a particular frequency, the complex impedance of my antenna system is sitting right here. Okay, whatever that is. Okay, that's my complex impedance. I'm not quite at the center here, so I know I'm going to have some measurable SWR, return loss, things like that. So the way we read these radially scaled parameters is we take and rotate, basically use a compass or something like that and take this point and rotate it up, equidistant from the center, up until we hit the prime axis. Okay. Once we hit that prime axis, then we can take and extend that line straight down. And where it crosses these radially scaled parameters, we can read off various things. So for example, that top line is SWR. See, it says SWR right here. Okay. And we can read off that we're seeing about a 2.3 to 1 SWR. Okay. We could see if we were right at the center, right? If we went straight down, our SWR would be 1 to 1. But as we come along this axis, we're at about 2.3 to 1. Okay. We also can read return loss, which is obviously mathematically related to SWR. There's a return loss of about 8.1 dB, okay? And reflection coefficient for both power and voltage, they can be read there as well. So it's just example of 4 of the radially scaled parameters that can be read right off of a Smith chart. They're all mathematically related, so things like a VNA can calculate them for you, but this is how it's shown on a Smith chart and how we did it before we had VNAs. Okay, well, that's before my time too. But this also gives you a little bit of a hint of something that, let's say I had my impedance here mapped out to an SWR of 2.3 to 1, but let's say I had an impedance that was right here. If I did the same thing, that would also be 2.3 to 1. So this is kind of giving you a little bit of a hint that if I continued this circle all the way around, that tells me that any impedance lying on that line is going to have the same 2.3 to 1 SWR. And that's kind of interesting. And we'll use that a little bit later on here. So again, let's talk about SWR now on transmission lines. Okay, so again, I've got a complex impedance here. And as I mentioned just on the previous slide, if we just draw a circle that crosses that line, centered at the center of the chart, what we're saying is that the VSWR and the return loss, okay, the magnitude of the return loss and the SWR are the same for any impedance anywhere along that line. Okay, so there's effectively an infinite combination of complex impedances that will result in the same SWR. Okay, so that's kind of an interesting thing. So as you can imagine, as that circle were tighter and smaller around the center, that SWR would be smaller. You get to the point where you're right at the center, okay, and your SWR is 1-to-1. So the larger that circle, again, the further you are away from the center, the higher the SWR is. Okay. So why do we care about that? Well, this interesting thing happens here is that when you add or subtract transmission line length between your antenna and your transmitter, you're effectively rotating around this curve on the Smith chart. Okay, if you add feed line length between your antenna, let's say you had 30 feet of coax and you added another 10 feet. As you add that coax, the complex impedance looking into that coax will rotate in a clockwise direction around this constant SWR circle. If we shorten the coax, we rotate the other way. Okay. Now, ideally, you rotate and stay on this curve. Okay. Now, if there's loss in the transmission line, then you wind up getting kind of a spiral. As you add more and more coax, you're getting more and more loss. Instead of following the circle, you're going to kind of follow a spiral and ultimately wind all the way up at the center if you had a really long piece of lossy coax. Okay. But let's assume lossless transmission line. Adding and removing transmission line will just literally rotate you around this constant SWR circle. So what's that also telling you is that ideally adding or removing feed line does not change your SWR. Okay, and you might say, well, I know if I change my coax length, my SWR does change. Well, that will happen when the coax itself is part of the antenna system. So for example, if the shield of the coax is part of your counterpoise system, either intentionally or not intentionally, then you're going to change the feed point impedance of the antenna by adding or subtracting coax, which is also going to affect things. But in those situations where your coax is not a radiating part of your antenna, ideally you're not changing SWR by adding or removing feed line. But you might also say, well, I've got an automatic antenna tuner in my rig, and it doesn't like tuning on 75 meters. But if I add 5 feet of coax, it does tune it fine. So it must change the SWR, right? It's going from one SWR that it doesn't like, and it's going to a different SWR that it can tune to. The reality is it's not changing the SWR. It's just changing the particular complex impedance that's being presented. And that your tuner might have a hard time matching an impedance that's here, but might not have a hard time matching an impedance that's here. Okay, but it's still the same SWR. Okay, so all these interesting little facts kind of come out when you start studying transmission lines and feed line lengths. All right, so what's interesting also is that one complete trip around this circle is essentially a half wavelength of transmission line length. Okay, so what that kind of implies is that if I have a transmission line length between my antenna and my transmitter, and it's exactly a half wavelength long, what that means is the impedance looking into the transmission line length is going to be exactly equal to the impedance of the antenna feed point. Okay, if it's not a half wavelength long, then the impedance looking into the coax isn't going to be the same as the impedance looking into the antenna itself, although the SWR will be the same. Okay, so every time you go a half a wavelength, you repeat the impedance. Okay, so again, that's one of the magic things with a half wavelength line. But now what's interesting is halfway around is a quarter wavelength line. And there's a lot of magic things that happen with a quarter wavelength line. You'll hear, quarter wavelength tuning stubs and things like that. But what the quarter wavelength line does is an open will be transformed into a short. Okay, and a short will be transformed into an open. Okay, so if I put a little T in my coax line, and I just hung a piece of coax off of the end of that T, and I left the end of it open, right? Didn't put anything on the other end of it. At a frequency where that's a quarter wavelength long, that will look like a dead short. Okay, so it could be a pretty effective notch filter for that one frequency. Okay, so so pretty interesting. You could actually have an open-ended transmission line that at a particular frequency will look like a short. Now this again repeats every quarter wavelength, right? So at one quarter wavelength, it'll do this transformation. Another quarter wavelength, you're back to repeating the impedance. Go a quarter wavelength around again, and it goes back and inverts. Quarter wavelength around again, and it repeats. So the odd quarter wavelengths do this transformation. The even quarter wavelengths do the repeats of the impedance. So again, all this is kind of shown on the Smith chart. It's kind of cool stuff. So let's take a look at adding coax lengths in an actual practical measured thing I did with my NanoVNA. So I got the same 20-meter antenna that I'm measuring with just gradually increasing the line length by certain amounts. Okay, so here's my starting point. That's kind of the plot that I showed you earlier. So there's my complex impedance, okay, going from 13.7 megahertz up to 14.7 megahertz. Here's my SWR curve, right? So now remember what we said, that we're just going to rotate around the center of the curve, but rotate around on that constant SWR circle. So what that means is that essentially every point on this curve is going to rotate it around its own circle around the center. Okay, so this point right here in the center, that's going to rotate it on its own little circle right here. The 13.7 point is going to rotate on a much bigger circle. Okay, so there's my starting point. So here I added about 3 feet of coax. So you can see my curve, the whole thing kind of rotated around. Okay, now it didn't go it didn't maintain its shape perfectly. And the reason for that is because the length of the coax is effectively longer at 14.7 megahertz than it is at 13.7 megahertz, right? Because at 14.7, it's a shorter wavelength. So the length of the coax in wavelengths or fractional wavelengths is actually longer for the higher frequencies. So that this point actually rotates around a little bit further than this point rotates around. So not only is this whole curve rotating around clockwise around the center, it's also kind of compressing a little bit, okay, as it goes around. So that was adding 3 feet of coax. There's another 3 feet of coax. I took that curve and rotated it around a little bit more, okay. Added another 3 feet of coax and I rotated around a little bit more. Now you'll notice the curve is a little bit tighter here now. It's like closing up a little bit more than it is over here. And again, that's because this 9 feet of coax that I added is more of a fractional wavelength at 14.7 megahertz than it is at 13.7. But now here's the really important thing. No change in SWR. Look at my SWR curve in all these cases. There's my white SWR curve with the minimum SWR right here. There's my SWR curve. There's the SWR curve, and there it is again. It didn't change in changing and adding these different lengths in coax. And the minimum SWR is still at the same point in every one of those, right? Because all these points just rotated around the center. Okay. But pretty cool stuff. Something maybe I didn't realize is happening, but this is what's going on when you're adding and subtracting coax length. You're changing the complex impedance, but you're not changing the SWR. So what can we do with that? So, well, one thing that's interesting is you can say, well, okay, I know I've measured at my antenna, or excuse me, at my transmit end area here in the shack. This is the complex impedance I measured here. Now, if I know the transmission line length between my transmitter and my antenna, I can essentially measure the impedance at the transmit end and then figure out what the impedance is at the antenna. Okay, so if we expand on this portion of the Smith chart, we can actually see that these outer axes, like with the numbers out here, are calibrated in wavelengths towards the generator and wavelengths towards the load. Okay. So remember how I said half a wavelength around is a complete trip around. So we're starting at 0 and rotating up. So there's 0.04 there. We go all the way around. Here's 0.49, and guess what? 0.5 would be right there, right? And same thing coming around the other way. There's my 0.04. I go all the way around. Here's 0.48, 0.49, and back. Okay. So we're using those scales when we rotate around. Okay. So again, I can measure the impedance at the transmitter and predict the impedance at the antenna. So if I measured the impedance here, I would rotate, at the transmit end, I would rotate towards the load, right? If I know the length of my line, I can say, okay, my line is this long, okay? And I'll just go by the right fractional wavelengths and say that's the impedance at the antenna itself. And that might be handy because ideally we want the antenna itself to represent a nice to match the transmission line impedance. So we really want our matching circuit to be at the antenna end. So, but you can do that by measuring the impedance at the transmit end. And if you know the line length, you'll know what the impedance is at the at the antenna. Okay. So you can use that to maybe design a matching network. Okay. So I want to talk a little bit about resonance and minimum SWR, because it's another myth that I want to kind of dispel here a little bit. And as I mentioned kind of towards the beginning, that resonance, the definition of resonance is that only means that the reactance of the complex impedance is 0. Okay, it doesn't mean that's where your minimum SWR is. Okay, so I didn't crop this picture right, but this is actually the center of the Smith chart. You can kind of see these circles, the constant resistance circles kind of going through there. So there's my center of the Smith chart. Okay, so this point right here is my 50 ohm point that I'm kind of pointing to. All right, so if we take a look at that, I got the marker, at the point that's closest to that. Okay, but now how many resonant frequencies are there on this curve? Right, there's one right there. Okay, and there's another one right there. So I actually have two. Now, if you want to think about it, this antenna and its coax is resonant at 2 frequencies. Okay, but neither of those are where the minimum SWR is. Okay, so the minimum SWR does not always occur, and oftentimes does not occur at the resonant point. So we're all kind of so accustomed to saying, hey, let me tune my antenna so it's resonant. And what we're really doing is tuning for minimum SWR, not necessarily tuning for resonance, right? Resonance doesn't mean minimum SWR, and they don't always coincide. Okay. And the reality is that you will generally get more efficient operation by operating at the minimum SWR point. Okay. And not the resonant point. But they're usually reasonably close, but they don't have to be. Okay, because generally the closer and closer you get to your ideal 50 ohm resistive point, the smaller the reactive component is going to be. But it isn't always going to be 0. Okay. So how do we set up the NanoVNA to measure an antenna or an antenna system, meaning the antenna and its feed line? Okay. Normally what that means is you're going to select the traces you want to look at. And you might just choose to put the SWR trace up, right? There's like the white trace right here, okay? And not have the others. I like using the SWR trace because this is what, we kind of grew up using for the last 40 or 50 years. I also like putting up the log magnitude on the NanoVNA. They just call it log mag, but it's really the log magnitude measured on channel 0, which is the S11. We could do S parameters, a whole nother talk on that, but it's really just the reflection coefficient. So it's the log magnitude of the reflection coefficient. So that's the yellow trace. That's this one right here. Okay. And I like having that up there because the SWR curve can tend to be a little bit shallow. Okay, whereas the log magnitude is a bit more sensitive because of the way it's computed, that more clearly shows you right where that minimum point is. Okay, it's a lot easier to see that minimum point is here, and sometimes the SWR is a little bit shallow. So the log magnitude of S11 can give you sometimes a clearer point of where your minimum SWR is. And then I like also having the Smith chart up here as well, okay, and for reasons that we'll see in a moment. So you would set up the NanoVNA to turn on the traces that you want. In this case, they're all measurements on channel 0, and they're just different. One is complex impedance, one's log mag of S11, and one is SWR, okay? And I turn the fourth trace off, okay? So turn your traces on, configure them the way you want. Then you go and you set your stimulus range. And I mentioned you don't want to set the stimulus range too wide, because any VNA has got a limited number of points that it will do. Kind of out of the box, most of the NanoVNAs were 101 points. Later firmware updates brought them higher than that. I've got one that'll do 401 points. There's some out there that'll do 601 points. And that's actually the actual points where the calibration is done, okay? And in between those, it has to do essentially an approximation or an interpolation between those calibrated points. So you don't really want to calibrate over the entire HF band if you're trying to measure an antenna on one particular band. You certainly can, but then it might make sense to have, and these NanoVNAs allow you to save multiple calibration slots. So you might have one that's set up wideband, and then others that are set up just for the bands that you're typically interested in. So you set your traces, set your stimulus range, run your calibration. Okay, again, the calibration sets up the measurement plane. I've got some videos on this, and this, again, it's another topic we can go into, but we'll just talk about it. It's just a good idea to calibrate where your transmitter connects. So so the NanoVNA is going to see what your transmitter sees. Okay, and then go make your measurements. Okay. So I'm going to play a video here. This is about 6 minutes long, and it's a most of video number 314. It's going to show you those steps that I just outlined, and also then show you how you can use the NanoVNA when you're adjusting your manual tuner. So sit back and watch this, and then we'll come back and talk some more.
We can see that the yellow trace is already set up to be the log mag of the reflection coefficient, so we'll leave that. The green trace is already a Smith chart, so we'll leave that one alone. So we'll reconfigure the blue trace to be SWR, and then get rid of the purple trace. So we bring up the menu, go to display, go to trace, and let's first just get rid of purple trace by touching on it again to get rid of it. And then we'll select trace number 1. The inverse text tells us we're selected. We'll go back and then tell it to be on channel 0, which is the reflection channel, or the S11 channel. And now we just have to go back in one more time to the format and hit SWR. Next, let's set up the frequency range we want to test. So we'll bring our menu back up and go back and back again and go to stimulus. In our case, I want to measure the 40-meter amateur radio band from 7 megahertz to 7.3. So I touch on the start frequency, then I dial in 7 M for megahertz. That will set up the start frequency, and then we'll go back in and select the stop frequency, 7.3 megahertz. And now we've set up the stimulus range that we want to test. The next thing we want to do is run the calibration. So we go bring the menu back up, go back and hit Cal, and go to reset the existing calibration. We can see that those calibration indicators have gone away over here. And then we hit calibrate, and since we're only doing a reflection measurement on channel 0, we only have to do an open, short, and load. So we start off by putting the open on the port and touching open, and next we put a short on the port and touch short, and then we replace the short with a 50 ohm load on the port and touch load. Once we've done all 3 standards, we can hit done and then choose to save it to a memory location. I'm going to choose just to save it to location 1. And so now we hook up the antenna. With the antenna hooked up, we can see our SWR plot over the 40-meter band. We can see the log magnitude of the reflection coefficient, and we can see the Smith chart. And we can use the jog wheel to move our cursor or marker to make measurements at various frequencies across the range, or we even have some marker functions to search for a min or a max. So for example, if I touch on marker number 1, that activates trace number 1, and I can go into the marker function and do a search and search for a minimum, and that will put the marker right at the minimum, and I can see that's at 7.216 megahertz. Now of course that's all we need to do if all we want to do is to sweep the antenna. But if we want to retune it, for example, we can leave these displays up and actually watch the reaction as we adjust the tuning on the antenna. So let's say, for example, I want to retune to be closer to the middle of the CW portion of the band instead of in the phone portion where it is now. So we can actually just watch the reaction on the VNA as I tune the controls on my antenna tuner. And this is where I find it handy to have the Smith chart shown on the VNA, because you can actually see how the controls on the antenna tuner are going to twist and roll the trace on the Smith chart, and it gives you a little bit better intuitive feel about which way to tune the various controls. Now the first thing I'm going to do is move my marker down to somewhere in the CW portion of the band, maybe around 7.07, 7.06, 7.05, something in the neighborhood. So to give me an idea, that's the point that I want to now try to optimize with the tuner. Alright, we'll start by moving some of the dials around here. Let's take a look at how the various curves move around. We can see as I turn my inductor up, I can see the Smith chart's kind of turning around in this direction. And we can actually see I'm bringing my marker on the Smith chart closer and closer to the center of the Smith chart. So I'm getting kind of close. But it's still kind of missing the mark a little bit, so we're probably going to have to optimize the capacitor here as well. So if we tweak on that a little bit, I can see I'm deepening the null there on the reflection coefficient, and I'm getting pretty close. So you can see with just a little more fine tuning on the controls of the tuner, I've got myself pretty darn good at my desired point right there. SWR is about 1.02. I'm sitting right at the center of the Smith chart. We can see that the yellow.
Okay, let's go on to the next slide here. So yeah, so hopefully that was kind of it's kind of a fun way to play with the NanoVNA and to really see what your tuner is actually doing to the complex impedance. So yeah, it's just kind of a neat thing to do. So also kind of get used to what the Smith chart's showing you and relate them to SWR and that type of a thing. So the last part of the chat here, I was going to talk about designing an L network, impedance matching network, and a little bit of extra credit here for those that might be interested. I know this is a bit more of an advanced topic, but I think it's helpful to kind of go through and see, this is how the Smith chart was used before we really had, kind of automated tools to do some of our calculations for us to design matching networks. We can kind of do it somewhat graphically. So let's run through that process. So an impedance matching network, like an L network or a pi network, is really just adding series and parallel inductors and capacitors to essentially move the impedance around to make it look like our desired impedance. In this case, our system impedance, or 50 ohms. Okay. So an L network is the simplest network to use, and its topology, which topology to use, is going to depend a bit on what the load impedance is. And there's these kind of yin-yang diagrams, if you will, that will kind of indicate what the most appropriate configuration of the L network is. I've got an L network tuner here. I've got my Tentec 238 tuner is an L network tuner, and it can switch between two different networks depending on whether the impedance is high or low. But if your impedance is somewhere in this kind of clear area here, then this network will work. We take here's my complex impedance, a shunt capacitor followed by a series inductor. We can match anything in this area down to where we want it to be. And conversely, this one here is a shunt inductor and a series capacitor. And then these two, again, a little bit different, show the other networks here as well. And then there's also these other subset here where you got two capacitors or two inductors. You can actually make an L network with two of those, and there's a limited set of complex impedances that they can match. And you'll find oftentimes that more than one topology will work. Okay, so if my complex impedance was somewhere over here, I could use this topology or this topology, right? Because both of those are in that white area. So why would I choose one or the other? It might be due to what components you have on hand, right? The value of the inductor and capacitor used in this network will be different than this one, and you might have one on hand and not the other, for example. Or you might want your matching network to be a high pass or low pass filter, right? So in this case, this matching network is more of a low pass filter. It will filter away high order harmonics. So that might actually be a good thing, okay? Because it's going to filter harmonics away. If you want your matching network to be a high pass filter, you might choose this, okay? So there's a number of considerations that you might choose to pick which topology, because in many cases you have a choice of at least two. Okay, so what happens when we add these inductors and capacitors? What happens to the impedance? How do we move it around, right? Because the idea is we've got an impedance that's non-ideal, it's not resonant, it's not at 50 ohms, but we want to move it to here. How do we get there? Okay, but we talked about adding elements in series and parallel. So when we add these components, we're going to move the impedance around on the chart. Okay, adding series inductors or series capacitors, meaning an inductor or capacitor in series with your load, is going to move us along the constant resistance circles like this. So if we add a series inductor, it moves us kind of this way, clockwise, along those constant resistance circles, and by an amount that you can kind of compute here. So here I went from a inductive reactance, normalized reactance of 0.8 to 1.4, which means I moved a normalized reactance value of 0.6 ohms inductive. Okay, multiply that by 50, that tells us how much inductive reactance I need to add, right? Adding a series capacitor moves us in the other direction along the constant resistance circles, okay, clockwise and counterclockwise, okay? And we can do the same thing, figure out how far we went. So, but that's all for adding series components. If we're adding components in parallel, we usually will do that computation by talking about admittance, right? Admittance is essentially 1 over impedance, okay? Because when we add things in series, like we add resistors in series, we just add them up, right? R1 plus R2 plus R3 gives us our total, right? But when we're adding elements in parallel, we add the inverses of them. So we say 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over R total. And then we can invert that to get the total resistance. So those 1 over resistance or 1 over complex impedance, we call that admittance. Okay, so it's handy to deal with things in admittance when we're adding the parallel elements. So the admittance is really just 1 over the complex impedance. And just considering each component itself, if we just have pure resistance, okay, then 1 over resistance is something we call conductance. And if we just had a pure reactance, okay, and a pure X, 1 over that would be the susceptance. So we call that B. But the reality is that if we have a complex impedance, it's not as simple as just inverting each element. It's a bit more complex than that, okay? So converting an impedance to admittance is really easy on a Smith chart. Mathematically, it's tricky when you have a complex impedance, but on a Smith chart, it's really easy, okay? So on a Smith chart, there's my complex impedance there. So if I want to convert that to admittance, I draw my constant SWR circle centered around the center. I bisect that circle with a straight line that goes through the center and touches at the other end. And then that value is the complex admittance. So in this case, I've got a 1 plus J 1.1 right here. And when I invert that, then the admittance is 0.45 minus J 0.5 Siemens. Okay. So we talked about the Smith chart and the impedance curves, both the resistance and reactance curves. There's also a way of designing a Smith chart that will show admittance curves, and it really is nothing more than rotating this chart by 180 degrees. Okay, it's just inverting the chart by rotating it around. Okay, so that's kind of what we did, on the previous slide, right? We went halfway around that circle, so it's the same kind of a thing. And what I've been showing here all along, but wasn't necessarily so obvious, is that this is actually a combination chart. Okay, all those red lines, red circles and the red arcs represent the resistance and reactance. But if you look carefully, there's also a set of blue lines in here, and they're centered the other way. Those blue lines are all the admittance lines, the conductance and susceptance circles, or conductance circles and susceptance arcs. Okay, constant conductance, constant susceptance. So as you can imagine, when we talked about adding elements in series, we walked our way up and down the constant resistance circles. When we're adding elements in parallel, we're going to walk up and down the constant conductance circles. Okay, so adding a parallel inductor is walking up the constant conductance circle that way. Again, we're on the blue lines now. And adding a parallel capacitor, we're going down the other way. Okay. So again, this is really easy to do with the combo Smith chart because those blue lines are there, and then we're reading the blue numbers over here to figure out how far we went. Okay. So how do we remember which way we go with all these things? So here's my corny little quick tip on how to do this. So when we're adding inductors, whether they're in series or in parallel, we're elevating through the real axis. Okay. So if we're adding a series inductor, we're going up through, and we're kind of going in this direction, where we cross the real axis. Okay. And then we're adding a parallel inductance. We're again elevating, through on the constant conductance circles. And even more corny, when we're adding capacitors, we see crashing down through the center axis. So a series capacitor is going along the constant resistance circles. A parallel capacitor is going along the constant conductance circles. So now you can kind of see that by adding series and parallel inductors capacitors, we can walk our way from any impedance on the chart, walk our way down to and zigzag our way to the center of the chart to create an impedance match. That's actually how it works. So let's go take a look at the process. So if I'm going to design an L network, the first thing I'll do is usually draw, and highlight my R equal 1 and my G equal 1 circles. They're going to help me here in a moment. Okay, this is where I want to get to, right here in the center. Maybe this is where my starting point is. Knowing my starting point, I can go to my little yin-yang diagrams and figure out what topology I want to use. So in this case, it's first a series inductor, followed by a parallel capacitor. Okay, so what we're going to do is add our series inductor, okay, from this point, and keep adding that until I hit my constant conductance circle. Okay, and depending on where I was, I might do that till I want to try and hit one of these circles, right? So I'm going to hit that constant conductance circle. Okay, now I've got the inductance value that I added, and then I'm going to add in this case, a shunt capacitor. So I'm going down on my constant conductance circles here, okay, until I reach the center. And again, reading off these scales on the blue axes here, I can figure out how much capacitance I added. And there's my LNC. So let's do a practical example of it, okay, just by computing this. Okay, so here's my practical example. Let's say I'm operating at 432.1 megahertz. I measured my complex impedance of 75 ohms minus with a capacitive reactance of 60 ohms. Okay, and normalize that, plot that on the Smith chart. Okay, that's where I am. So that's where my complex impedance is. This is where I want to get to. Okay, so I'll look at my yin yang and say, okay, I'm going to use this topology. So I'm going to start off with, going from my load, I'm going to start with a shunt inductor and then a series capacitor. So let's go to the next step. So I'll first kind of, again, highlight my R equal 1 circle. And I'm going to, now I'm adding a shunt inductor. So that means I'm going along my constant conductance circles, okay, like this blue line right here. I'm going to follow that all the way up until I hit my R equal 1 circle. Now I got to go take a look at how far I moved. So if we look down here, if we follow this down, that's between 0.3 and 0.4. So it's about a 0.32. And so that moved from there to 0. And then from there up to this point here, which is on the 0.5 line. So I basically moved a normalized susceptance of 0.82 Siemens, right? So that's how far I moved. So that's how far I went. I can invert that to get to the complex, the normalized inductance of 1.22. I multiply by 50. So this tells me that I want to add 61 ohms of inductive reactance. And knowing my operating frequency, I can then take, that's the reactance I want, 61 ohms, divided by 2 pi times that 432.1 megahertz. It tells me my inductor is 22.5 nanohenries. Okay, so that got me up to this point. Step 3 now is I want to add my series capacitor. That's going to rotate me down along my constant resistance circle to the center. So I rotate that down. I can see that I added 1.2 ohms or 1.2 normalized ohms of capacitive reactance, multiply that by 50. Again, that gave me 60 ohms of capacitive reactance. And again, knowing my operating frequency, I can compute the capacitance value from that 6.14 picofarads. So now I've got my L matching network that took my complex impedance from my antenna and now transformed it to look like a 50 ohm resistive input impedance. So that's how you design an L matching network using Smith charts. I know it's a lot easier to plug numbers into a calculator and just get it, or a simulator or something like that, but this is the way it was done graphically before we had those tools available to us. And it's just kind of cool to see how it all works. So I've got a number of videos on my channel that are related to NanoVNAs in terms of the basics and things like that. I've got, number 312 is the basics of what a VNA is, what's a VNA itself, and then talks a bit more about the NanoVNA. I've got a whole video dedicated to and talking about how and why we do a VNA user calibration. Another one, 314, is the one that I kind of showed you, is measuring an antenna, observing that tuning process. 316, how do we measure antenna coax length with the VNA? Okay. Number 325 talks about the effect of adding transmission line length. That's what the one where I got those pictures that I showed you where we added 3 feet at a time. Number 326 is how to measure the impedance of an unknown hunk of coax. Okay, and then also there's another one, 334, is showing how to tune a repeater duplexer with a NanoVNA. So, but it's just a couple of examples of VNA videos that I've got available. So in summary, Smith chart is a pretty highly useful tool for looking at SWR, looking at return loss, doing transmission line impedance transformations, understanding the effect of adding or subtracting transmission lines, maybe designing matching networks and things like that. And there's a whole lot more that you can actually do with it, but this was just kind of what we touched on here today. And a little bit of a shameless plug again for my YouTube channel. It's just youtube.com/mycall, W2AEW, and my contact information.